listen up. On this particular problem, number 11, this is what we call a lab-based problem because you have data from a lab that you have to acquire, in this case, from a graph, right? Now, sometimes when you're acquiring data, you're acquiring it from a table. In this case, you're acquiring it from a graph itself. And so when you read the graph, they're going to do this on purpose. They're going to make the graph so it's not like Physics B or particularly pre-AP physics where the data comes out exactly on one of the lines, all right? Or like in math class, it always comes out perfect, right? Okay, so this is the real world. So when you read this across here, your information may not be exactly the same as anybody else's. Now there's going to be a range which they'll accept. Acceptable reading of the graph, and then an acceptable answer from that data. And then if you use that data down below, it's going to make your answers different from other people's, right? But they ought to be reasonably close. What they'll generally do is, like if the acceleration is supposed to be 15, they'll say, well, anything from 14.5 to 15.5, a reasonable range. That if you're outside of that, then obviously you did something wrong, okay? All right, let's look at this problem 913. Do you?
It's like, this is, I don't know, it's mostly linear.
Mr. Ruin.
You get this, like, same.
Mr. Ruin.
Yes.
When we work B, can I do it? Because I think I figured it out.
This one?
Yeah.
Okay. Well, let's take a look at it. I haven't even looked at it yet. So, problem 913. Determine the spring constant. Okay, we can do that, right?
Well, we all disagree, so I guess not.
How can you disagree?
Because some did energy and some did forces, and some got 2 mg and some got 8
It's a difference of a factor of 2.
Okay. 2 blocks
Yes.
shown, M and 2M. Block 2, and block 1. Block 2 has an ideal massless spring attached to one side. Block 1 is placed on the spring as shown. The spring is compressed distance d. So before it looked like this. So the distance from here to here is d. Express your answer to all parts. The question in terms of physical constants. Determine the spring constant. Okay, so what were the methods we were attempting?
Forces.
Okay, it looks like it might be forces because in forces we have a spring force, right? Spring force equals kx, or maybe it's energy. Because energy, you have spring potential, which is 1/2 kx squared. All right? So, if we apply this with forces, then what are the keys to applying this properly?
Sum of forces is 0.
Okay, when we're here, the sum of the forces add up to 0,
Yes.
right? So we have 2 forces. We have an mg down, and we have a spring force up. And these two must be equal, so therefore this must equal mg. And you notice I've neglected the negative sign. I've neglected the negative sign because I've already drawn what the direction is, right?
Mr. Ruin?
Yeah.
Isn't it? Okay. Sorry.
All right, so that's k, d equals mg, so d ought to equal mg over k. Drat. So k ought to be mg over d.
Well, if you use energy, you get 2 mg over.
Yeah. There
Hmm.
should be a
You can't
reason.
combine
All right.
force like that, can you?
But it's a different system. Like,
Because
I would
you
Well,
have
you don't have the height.
there's some reason one doesn't work.
Spring
They said the height was D.
All right. So let's see. Can we do this with energy? If we place the block here,
Oh, yeah. Anastasia has a point.
Yeah, because the D we were using was changing the spring, and it has to be a whole.
Yeah. The D we're using for the energy thing is the little d, not the.
And it has to be the whole height
Well,
for
but
it to work.
if they said the equilibrium.
all right, well, let's
point is
just
0,
see. If we start here, first of all, can we use conservation of energy?
Yes.
Are there any outside forces acting on this object?
No.
Well, sure there are. There's gravity and there's spring force. But are those acceptable?
Yes.
Why? Because they're conservative forces. And we're going to handle those forces in terms of their energy instead. Okay, so there's no friction, no normal force. Is there normal force? No spring force, right? Okay? All right, so let's see if this works. All right, so what kind of energy do we start with?
Energy.
What kind do we end with? Okay, you're calling this equal 0?
Yeah.
You get.
All right.
Would you have to consider a negative MGH for the other mass?
But it's not moving, right?
So high.
Oh, no.
Now, technically, yeah, we're just talking about this object right here, right?
MGD.
Okay, yeah.
Okay, so right here, then from here we have spring potential, right?
Yes.
Uh-oh.
Do you understand our plight?
Our plight is that energy at location 1 equals energy at location 2.
MGD.
mgd equals 1/2 k
D squared.
d squared.
Take out the square of the D
And the D and the
It would
K
be
is
2.
2mg over D, and you don't know what to do. Yeah.
Yeah, because that's what I thought.
Yeah, that's the problem.
Just kind of sneeze and pretend.
I haven't looked at the answer yet, but my gut feeling is that this one is correct. I'm thinking it has something to do with the fact that, remember when we did springs and we said that when you, did we talk about this, when you hang something on a spring, that you have a new equilibrium position?
Yeah, and halfway between, so it'd be 1/2 MGD.
Yeah. And so let me look and see. Everybody, well, unfortunately, I had a bad feeling about this method because there's some things that I'm not sure about. One of the things I'm not sure about is the whole thing. Remember when we had a mass on a spring, and we talked about this, I believe, when we talked about energy already, that when we add a new mass on a spring like this, I hope we talked about this, this is your new equilibrium position, right?
Yeah.
We talk about that?
Yeah.
I thought we did. So here's your normal equilibrium position, okay? But when you add a mass to it, x equals 0 is right there. There's your new equilibrium position. And when you do that, you can neglect the gravitational component, and when it oscillates back and forth, it's going to oscillate between here and here, max amplitude and negative max amplitude. And all you have to worry about when it goes back and forth like this, it's going to be exactly just like this problem where x equals 0 here and oscillates back and forth between A and negative A. Exactly the same, where all you have is spring potential, kinetic, and spring potential, and oscillates back and forth between them. And over here you can do the same thing. Spring potential and kinetic, and oscillates back and forth between them, and you can neglect gravitational, because all the gravitational does is you're accounting for it by setting up a brand new equilibrium position. Okay? I think that's maybe the issue here. I'm not positive. I need to investigate this more because it sounds somewhat vague. There should be a better way to explain this. That when you put this mass on here, this becomes our new equilibrium position, and
But that doesn't really.
No, it goes past the equilibrium position.
but the problem is, see, is we're working between two equilibrium positions. We have a situation where it's not on there, and then it's on there. Does that make sense?
Mr. Gruen, like
Wouldn't it be half?
Would it?
Go ahead.
Because if it goes down to that point at the bonus, it would be in the middle. Equilibrium position.
But that isn't the new equilibrium position, right? When it's at its max
This
compression,
is,
it's
no,
past the
this is
equilibrium.
the equilibrium position. Because equilibrium is when the forces cancel. And that's the spot where the forces cancel. It doesn't matter whether this mass is here or not. It's just we're talking about, because that mass isn't doing anything. That's the floor in the problem. Okay? Sunhang, what was your explanation? Is this is only half of the distance
It
d?
said in the other picture that it would be, it
You're
would
saying
oscillate between that point and that point.
Just do force.
The equilibrium would be in the middle, so it would be 1/2 d instead.
Oh, I see what you're saying, but I don't think that's correct. Because the equilibrium position is defined as when the forces all cancel. So this is our equilibrium position right here, because the forces cancel when it's right here. Man. I have to think about this one. I don't have a real good, solid physics explanation on why this doesn't work. And unfortunately, the key just says, a lot of students applied conservation of energy. That is not the correct method, is what they say in the solution. And then they said, but if they tried conservation of energy and they set up, this, they got one of the 2 points. That's all it said. Yeah, that's very vague. That is extremely vague. I'm going to have to think about this one because there ought to be a way for us to explain for sure why that's not going to work. And I'm sorry that I don't have that explanation off the top of my head.
Mr. Bruin, my answer for B worked so beautifully.
Yeah, no, we can't break physics. All right, let's finish this one out because this one appears to be our most complicated one. All right, it says, later the 2 blocks are on a frictionless horizontal surface. I need to circle this one as one I need to...
Unicorn's blood.
Mr. Brown, I like your shirt.
Thank you.
Purple is my favorite color. So you should use purple.
It says the 2 blocks are now on a frictionless surface. So surface 1, or object 1, object 2, 2m, object 2, and then m, object 1, spring attached here. It says block 2 is stationary, block 1 approaches at a speed v naught. As shown above, the spring compression is maximum when the blocks have the same velocity. Explain why this is so.
Let's let Andy do it.
Bad
She
shit.
figured it out.
Please, because it kind of makes sense.
All right, Andy's got some crazy explanation. Let's critique it.
You want me to do it on the board?
Yes, come on the board.
It may be wrong, and I'm willing to accept that because, like, their simplistic explanation on the exam that's very vague makes sense too.
Mom.
Is anybody colorblind? Just talk.
Yes.
Really?
Yeah.
See? So I don't know why you read. Okay. So I did E1 equals E2, and I think that's where Mr. Bruin says I'm
Bianca doesn't like
accepting
cats and
it.
mangoes.
Okay, now here's my deal. Is E1 equals E2?
I did it like a collision thing. Well, since it is a collision. It is a collision.
Is it? Okay, we have a collision. Normally with a collision, what kind of physics do we use?
Momentum.
Conservation of momentum. Why?
Because
It's not
But we
elastic.
used synergy before.
Energy's lost.
I mean,
Mr. Brown,
Momentum's always.
she I think she had it
Why?
right. That only makes sense.
But
Why is it that during a collision we use conservation of momentum most of the
Because the
time?
mass,
That's easy.
you don't have to worry about it.
Okay, now you're missing the big point. What's the big point? What's the big deal about conservation of momentum? Objects interacting, and when objects interact, they both apply an impulse or force on each other, which is equal and opposite. So the impulse is equal and opposite. So therefore the momentums of each of them change, but equal and opposite, right?
Yes.
So if we connect all of them in a system, then the total momentum of the system will not change, right? As long as we have no net outside forces. Now we have gravity, and we have normal force, which cancel on both of these, and no friction, right? So we ought to have conservation of momentum here, right? Okay.
Wait,
Andy,
Andy,
you just wrote that
missing
wrong.
an MV.
I know, but
You should
I know it's 3 and we're-
Why?
but it works.
And that's not energy.
You should
That's-
explain
it should be
it.
1/2 kx
Oh,
squared.
that's right. Okay.
You should explain as you go.
Okay, now, before we go too much further, Andy has said that in this collision we have conservation of energy. Will we?
That's a very good
That's-
question.
Well, it didn't
Why
work for
would
A, so.
That's not when they crash. It's the
Won't we though?
It's frictionless, right?
Not exactly.
Because
Okay, is it frictionless? So no non-conservative forces, right?
Yeah.
Well, wait a minute. We do have a force in between these two, but it's a spring. Is that okay?
Okay.
That's okay because that's a conservative force, right?
Yeah.
All right. Now remember, in momentum, you can have any kind of forces between the objects. Any kind at all. Friction, tension, normal, whatever. We don't care
But
as long as there are no net outside forces. Now, when you have conservation of energy, you can't have any non-conservative forces. Okay? But all we have going on here is a conservative force. So we'll see. Let's see if this works.
Okay.
All right, so you're saying, go ahead.
Okay, so then, since it wants
Wait a
to
minute,
know
hang
the
on.
maximum,
We got a 2m here, right?
It was three.
Since
yes.
the objects are moving together at that
Collision.
point,
3.
Ah, okay, so you're saying that at the beginning we have kinetic energy only,
Yes.
then afterwards when they're stuck together, we have 1/2 3m v squared, and that v is a different v, right?
Yes. That should be
Okay?
they're the same.
And we have spring compression.
2. Right.
Does that look good?
Yeah.
Okay, because we all have nothing but conservative forces, right?
Yes.
Yeah.
So we're okay.
I don't
Okay.
think this is going to work out anymore, but I'm going to keep doing what I thought I
Huh?
was right. Anyway, maybe it'll work out. So then, since it's doing, it wants to know the maximum. When I was in calculus last year, when we did maximum, we took the derivative. So,
Derivative with respect to what?
kx, I just took the derivative.
See,
that doesn't.
That's
on
why
the
it doesn't
left,
work.
we
I'm going to
derive
continue
with respect to
x, and then on the right is b. I know, but
All right, so stop.
False.
Okay, stop.
Falsities.
Okay. Up until this point, we have happy face. Because the kinetic energy of the one block
And then you break
equals the
magnets.
kinetic energy of both plus the spring potential between them, right?
right. Okay.
Okay, all from here to here, we have happy face. Everybody's happy. Okay, now, from here, let's stop, because this is on video. No, stop.
So, Mr.
But he's
Barron,
going to take that out.
if I have friction,
Uh-huh.
right, can I just say force times distance to consider that energy?
Not, well, that would be the work. So what you could do is if you have outside forces that are non-conservative, then what you have is that the energy before
Equals.
plus the work that's done equals the energy
Could
afterwards.
you see that happen?
Or the work equals how much the energy changes.
I tried. Do you see? Wait, we're just looking for.
Fabiola, you have it?
It's on the ground.
Oh, man.
You were so excited too.
Well, you got halfway there.
Why don't you keep trying? Just don't do that what you're trying to do.
I know, it makes sense.
You got happy face up to that point, so it's
Look
okay.
at this.
Why don't you change the name to a D or whatever the
I
other
tried.
one?
Hey, I was hoping none of y'all would find out.
We had quite a few people say that as well. Yes. All right, here we go. We had a group of people saying this. Oh, you erased it. We're going to need that later.
Wow, you can rewrite it.
Bummer.
Can we just write that last line?
Yeah, we can. We can say that during the collision, E1 equals E2, the kinetic energy of block number 1 equals the kinetic energy of both, plus the spring potential, which is 1/2 mv naught squared equals 3/2 mv unknown squared plus 1/2 k x squared, right?
Yes.
Okay. That should be true during, well, technically during any part of the compression, right?
No, because at that says you're at the same final velocity
Ah, that's correct. This is only during
during that.
max compression.
But you're supposed to,
All right, yeah, because these two velocities won't be the same. We said that the velocities are the same. All right, now, we had quite a few people doing this kind of explanation, where they're saying something like, okay, but the kinetic energy of this turns all into spring potential energy. Okay?
that'd be kind of cool
Now, that would be okay
if it was.
if this was locked in place. Okay, is this locked in place?
No, and it's.
It is free to move. So as soon as this thing hits that spring, the whole thing's going to start to move until we reach maximum compression. So it's going to go like this. Okay, here's my little acting job here. All right, so this one's going to come like this. As soon as it hits that spring, this one's still going to approach this one, but this one's going to start to move, right? And then they'll reach this same speed, and then this one's going to take off faster than this one. Does that make sense? So they're going to come in and they're going to go like that. Now this one's smaller, right? When a smaller object collides with a larger object, what kind is probably going to happen?
It stops.
It might stop,
Or it might explode backwards.
or it might bounce backwards, right?
I think bounce would be better.
Okay. Yeah, it's
Like Georgia.
going to
against-
maybe bounce backwards. We don't know. But if it's a very large object hitting a small object, then this one will just slow down a little bit, right? And this one will take off. Okay. All right, so here we go.
Spring will make it.
A lot of you made this much, much harder than it needed to be.
I'm sorry.
Obviously.
Look, when this is at maximum compression, it's neither approaching this one anymore, and this one's not going away from this one, right? Does that make sense?
Yes.
That's kind of the definition.
When you have maximum compression, it's not approaching the other one anymore, and the other one hadn't started going away from it, right?
So we should use forces.
Or
Wait,
words.
what is that called?
Use
You
your
could
words.
have used
What?
these words. When the v relative, or the relative velocity between the two, equals 0, block 1 is no longer approaching block 2. Okay? It is stopped relative to block 2. Okay? So they have to have the same velocity, the same relative. They have to have the same velocity and no relative velocity between themselves. Very simple.
That's all we had to say.
Yes.
Except 1%.
Now there is another way to explain this. You could say also that when the relative velocity between the two blocks is 0, you're at maximum spring compression. Okay? And when you're at maximum spring compression, the total kinetic energy will be at a minimum. Now, I don't think that explanation is nearly as straightforward. I think the straightforward one is just when you're no longer approaching the other one anymore. So therefore you're at max compression. Okay?
No, you said spring. You said it was in central line.
All right.
Anyway.
Now it says determine the maximum
Would you
compression
still-
of the spring.
Would you still need that?
This? No. All you do is say,
Just write that.
you write that. I think it was only worth 1 point.
Yeah. Which is frustrating.
Okay?
For part C, you need it.
Okay, now part C. Part C says calculate the max compression. Okay, first of all, this is not a forces problem, right?
Right.
Okay, this is not a kinematics problem. But this is a collision, so therefore conservation of momentum. So what does that tell us? P1 equals P2. How much momentum do we have to start?
MV naught.
mv naught. How much momentum do we have afterwards?
3 MV final.
We have 3mv question mark, whatever that is, right?
Therefore, you can solve for the question in terms of V naught.
So we know the v question mark equals 1/3 of the original. Now that should make sense. Whenever we have a totally, what kind of collision is that when they're fully compressed? What kind of collision is that?
Totally inelastic.
It's a totally or completely inelastic collision. At that instant in time, it's lost its most kinetic energy. And that's why that previous explanation works. When you have the maximum compression of the spring, you've lost as much kinetic energy as it's going to lose. It's all gone into spring potential, or more of it's gone into
Does
spring
that say V
potential.
question mark?
Yes, V question mark.
Throwing you off.
That's the one we don't know.
Oh, I just wrote.
Now, this has not helped us find the total spring compression, has it?
Nope.
No.
All right, so we need something else. This is an okay statement. It's just not our answer. So then I refer back to Andy's idea.
Yay.
Andy's idea is useful because in this collision, we have conservation of energy because we have a conservative force between them. Since we have a conservative force between them, this is true. Okay? Now, if that is true, notice what we know. We know that and that and that and that because those were all given, and now we have this because we just found it, right?
Yeah.
And so then we can find x. So we have 1/2 mv naught squared equals 3/2 m 1/3 v naught squared plus 1/2 kx squared. What's that?
Ng over d is k.
And k is
Ng over
mg over d x squared. Okay, so several things can happen here. I can get rid of a half. I can get rid of an m. I'm left with a v squared equals 1/9 v naught squared. Oh, this is a v naught as well.
times 3.
Oh, times 3. So this is 1/3. Thank you. I missed that.
Ridiculous.
And then I have a plus g over dx squared.
Where'd you get? Wait.
What? Wait, don't the threes cancel out?
This one's squared.
Oh,
Be
yes.
careful. That's in
Oh,
parentheses.
okay. I see what's happening.
Yeah, don't forget your parentheses when you have square. All right, so I can move this to the other side. So I end up with 2/3 v naught squared. And I can multiply by a d and divide by a g. And I can square root that, and that's x.
Yeah, I would have never substituted.
That part
I need a
E.
second. I need a second. That's all I need.
Part,
Now let's check to see if that's right. 2/3 d over g square rooted times v naught. Yes. Now you don't have to make this any prettier than this. Now if you want to spend time doing that, please do it after the exam. Okay? Don't waste any time making this any prettier on the exam, just because you don't have the luxury of time. Okay? That's mathematically correct. All right, last one. Determine the velocity of block 2 after the collision when the blocks have been separated from the spring. Now, this is a collision, obviously. We're looking for final velocity. This screams conservation of momentum. So, yeah, exactly. So how much momentum do we start with? I think we said mv naught. How much momentum do we end with? I end up with mv1 after the collision plus a 2m v2 after the collision because they're no longer connected. Now, this is a beautiful equation. Unfortunately, we know, well, we can cancel these, right? So we have v naught equals v1 plus 2v2. Unfortunately, that's the only one I know. So I need another equation.
Alright, energy.
You need a way to connect them.
Electrostatics.
Yeah, impulse is not going to give us anything new, right?
Not till we actually.
Not forces,
Energy.
not kinematics. What kind of collision is it?
Elastic.
It's elastic. So let's rewrite this. But now we're going to rewrite it for this type of collision. Actually, not this type of collision. For this, where this is before the collision and this is after the collision, instead of before the collision and during the collision. Okay? So before the collision, I have 1/2 mv naught squared. After the collision, I'm going to have 1/2 mv1 squared plus 1/2 2m v2 squared.
There we go.
Okay? That works great, right? Halves go away, m's go away. I'm left with v naught squared equals v1 squared plus v2 squared. With a 2 in there. Would have got it wrong again. All right, so there we go. So now we know this. So we have a system of equations. Now this will work. But does anybody remember the special trick I told you? That before and after, during a elastic collision, that this is our first equation, this is our second equation, but this always gives us the same thing. And that same thing is that the v1 minus v2 is going to equal v2 minus v1 before the collision and after. Okay?
Wait, what?
That's what he taught us.
The velocity of approach is going to equal the velocity of recession,
Okay.
right?
Yes.
That's the way most students will remember it. Velocity of approach equals velocity of recession only in an elastic collision. Now, you can solve it this way. This works great, but these squares make it a lot harder to solve, right?
Yeah, we
You're
went.
going to end up with a crazy big quadratic to solve. It just takes a while. It's not wrong, it just takes a while. So, what was our original velocity?
V naught.
V naught minus 0. Our velocity of approach is V naught. So what must our velocity of recession be? V naught. But this time it's going to be the velocity of 2 minus the velocity of 1. Now why will it be 2 minus 1? Because velocity 2 is going to be going away from velocity 1, right? Block 2 is going away from block 1. All right. So that's V2 minus V1. So if I take that,
And I've got that other like linear system.
oh, you've got this. Yeah, if you graph this linearly and graph that linearly, is that what you did?
No.
Oh.
I'm just, well, you could substitute.
Yeah, substitute is easy. Let's move this to the other side. V2 equals V naught minus, no, plus V1, right? Hey, which one are we solving for?
V2.
Correct. Okay.
So V1 equals.
Then we want V1 equals V2 minus V naught, right?
Yes.
Take that, plug it in up here.
No.
No?
That's right, that's right.
That's right. Move this to the side, move this to the other side, right?
Just trying to crush your dream. Hey, what I just wrote?
So I get V2 minus V naught plus 2V2.
2 thirds V naught.
So I get 2 V naught equals 3 V2. So V2 equals 2/3 V naught.
And we're done.
Now let's check it. If I take this and I plug it in right here, what's V1 going to be?
Negative 1/3.
Negative 1/3.
V1 equals negative 1/3 V naught. Now, do I have a velocity of recession that equals my velocity of approach? Velocity of approach,
Yes.
Yeah.
yes. And does it make sense that the little one bounces off the big one?
Yes.
That makes sense, right? That it should maybe recoil. The force between the two will be the same, so the big one will speed up and the little one will slow down, but the little one has a larger acceleration than the big one, so it'll have a bigger change, right? So it actually comes to a stop and recoils. There you go. All right, don't forget, when we have a rotating object, if it's rotating like that, okay, which way is the angular velocity vector?
Left.
Out. Of the
Oh, well, this is intended to be three-dimensional. There's the axis.
Okay.
Oh, up. It would be up.
Oh, because of the right hand rule?
Yeah, there you go. Angular velocity vector is up. We got the right-hand rule. We curl our finger around the direction it's going, and the angular velocity is in the direction of our thumb. Okay?
It's like thumbs up.
All right? So which way is the angular velocity for Santa?
Down. Right?
Yeah, because we go
we
clockwise
rotate
with the
it.
velocity, right?
If I'm looking at a map.
Okay, if you're looking at the globe,
Oh no, I rotate this way. So it's up.
here's
I'm
east,
sorry.
here's
I'm
west.
sorry.
Here's Santa. Ho, ho,
We
ho.
rotate east.
So you rotate this way.
I'm sorry.
So the angular velocity for vector, angular velocity for Santa is upward. Angular velocity for the poor little penguins is down for them. Okay?
You drew the arrow up.
It's correct. It's down for them because they stand this way.
And so Santa's lighter.
Right? So if you're on the South Pole, the angular velocity vector points that way. When you're looking at the South Pole, it points down. If you're in Santa looking at the North Pole, it points up. Right?
How would that affect us if we rotated like that instead of like this, like they did?
Like if you're on Uranus.
Yes.
Yes, it's the other way.
There was a if it had the vertical spin.
Uranus rotates like this. Its equator is horizontal like that.
Okay.
It just points horizontal.
Oh, that's odd.
Will we feel
It is
different
odd.
when wait?
Would
it
we
points-
feel different? Heck no.
We would be
Because
dead.
remember, we're just drawing it.
What?
There's not a real thing
Okay.
there.
I like Andy's explanation.
I love how your
It was
penguin's a
very-
person.
Yeah, it's the Penguin. You know, Batman.
It's Alfredo. Oh. I don't get it. No, it's
Anyway,
That thing's scary.
All right, now let's not forget cross product.
We won't.
I bet you will.
I think I
Oh,
will
the
too.
wrench. You
Okay,
love
the
the wrench.
magnificent wrench picture. If you're rotating this way, you're rotating this way, which way is the angular velocity vector?
Out of the
Out
box.
for it.
Out of the board, and remember that torque equals what?
R cross F.
R cross F. And everyone in cross product, the order is deadly important because it's R out to the place where you're applying the force. Which way are we applying the force then?
That way.
Which way is that way?
Down.
Down?
No.
Upwards.
Oh, wait, yeah.
Sydney.
So remember, lefty loosey, righty tighty, right?
I say that every time I unscrew something.
Okay.
Every time?
Yes.
Excellent. Okay, now the angle between these two vectors, please be careful. This vector points this way, this vector points up. Here's the angle theta in between, right? It's R cross F. R cross F, so your thumb points out of the board. So the torque is out of the board. All right, got that going for
What
us.
do you mean?
All righty.
Wait.
So don't forget, this is also RF sine theta.
R cross F.
Everyone?
Yes.
This right here is the same thing then as RF perpendicular, right? This is the perpendicular. Or you could write it R sine theta F, in which case, remember this one, that's the perpendicular radius right there. That perpendicular radius thing is going to come in real handy. Remember I told you that. It's going to come in real handy when we talk about angular momentum. Okay, so here's a little backhanded way of getting angular momentum. Here we go. Momentum equals mv, right?
Yes.
Okay, is everybody okay if I just multiply both sides by r?
Sure.
R and R.
Shock the world.
Got it? And we know that V equals omega R, right? I'm going to take that and I'm going to plug that in here. Okay? So I get PR equals M omega R squared. Got it? Now I'm going to rewrite that to MR squared omega. What's MR squared?
I.
That would be I, right? So
I omega.
R equals I omega,
Which is mass equivalent and velocity equivalent.
right?
Wow.
Now, yeah, exactly right. Now the only thing that I've done here is this thing, I haven't really derived this exactly right, you know, with all the correct math, but this is close enough to give you the idea that if you have a momentum that has a radius, a momentum with a radius is equal to I omega. Now, a momentum with a radius we call angular momentum, okay? Now, unfortunately, that's capital L.
Of course. Why not?
That's not nice.
Yeah, angular momentum,
So it's out.
okay?
So momentum is not
What's that?
momentum is not rho.
Let's put it into practice.
Momentum is not rho, it's d. That's correct.
I always have.
All right?
Oh, you.
Wait, so did I?
Now,
It's not?
angular momentum is, okay, let me rewrite this. This is really MVR, right? Okay, now when we do this mathematically correctly, there's a cross product in here. Okay, so angular momentum technically is R cross MV. That's angular momentum. R cross MV. So just like we have torque, R cross F, angular momentum is R cross the linear momentum.
But so your
Oh, it makes sense.
derivation would be correct if you started with that, right? You just R crossed.
Yes.
Be legit.
Because basically,
It's sort of
isn't
legit.
torque
Math people will be
angular
mad at me. Actually,
force?
physics purists will not like this.
Yes.
But this is nice and simple to kind of show you the relationship. Okay? All right. So r cross momentum, radius of the linear momentum, okay, gives you angular momentum, okay? All right, so there are several ways to write this. One way to write it is this, r cross mv. One way to write it is r cross linear momentum. Or you can write it I omega. Okay? Those are our three ways to write that. Now that ought to make kind of sense, because remember when we have linear momentum, it's mv. When we have angular momentum, we should use the angular equivalence here, right? Which the angular equivalent of mass is moment of inertia, and the angular equivalent of velocity is omega, right? So that kind of makes sense. So there we go. There's angular momentum. Dun, dun, dun. All right, but how? Let me see, hang on. Is that what I wanted to ask?
That's a good question. Why? Why? You know.
Oh, a couple things before we go on. All right, this number here, this number here, this number here. They all imply a center point, okay? Radius implies a center point. Moment of inertia has a point about which we're calculating it, right? So it's important for us when we calculate when we calculate angular momentum that we know where our point is about which we're calculating our angular momentum. Now there may be an exact point where something's rotating. In that case, you generally will pick that point. So it's the easiest. All right, what are our units for this?
We're gonna say kilogram.
I would say we have a kilogram. I would say we have a meter per second
Times a meter.
times a meter.
Kilogram meter squared per second.
So we have a kilogram meter squared per second. And that is our units for angular momentum. There is no special name for that. Okay, just kilogram meter squared per second. That's it.
Like a Bruin.
No. They haven't caught on to that yet, so I've been pushing for that. Push harder.
It sure does. Like.
All right. Now, which way is the angular momentum? So, like, for instance, if we're talking about the Earth again, so here's the Earth, okay, it's rotating around that way. Which way is the angular momentum of the Earth point?
We'll call it up.
Okay, it's going to be whatever the angular velocity vector points, right? Just times the scalar of moment of inertia. Or you could do the r cross mv if you want. But it's easiest just to say, look, this is the direction of omega, so that's also the direction of the angular momentum. They will have the same direction.
So, okay, so momentum is in the direction of omega. So this still works.
Angular momentum is in the direction of omega, so this still works.
It's like
Okay?
if you think about
If you do it with a
R
reference.
radius, it's rotating this way.
Okay, now, you need your calculators. Oh, I just erased all our equations.
Sorry.
I will rewrite them. L equals R cross MV. L equals R cross P. L equals I omega. Now, you see that we have three different ways to calculate this. Really, we have two ways. These are the same. Okay, those are the same. Notice if we have a lumpy mass object, then this is going to work out really nice, right? But if we have a continuous mass object, like the Earth, a sphere, or something like that, then this is going to work better, right? Because we have the moment of inertia of that object. All right. So, let's say we have a car. Yes, we do. A car traveling this way at, what do I have it down here at? Traveling at 20 meters per second. It's a 1,000 kilogram car. And here's our point down here, point O. Okay? You know what? Let's not do that first. We'll do this one first. Here's our point O. Point O. What?
Your 1,000 kilograms looks like Pookie.
You know what? That's what my car name's gonna be.
It does look like
I promise you. I
So
will
you
remember
name your
you
car
forever
Pookie.
because that's gonna be my car's name.
It's kind
And-
of cool.
I can't even write it now.
There you go.
That's so no fun.
It is funny.
Okay, Pookie is traveling around a circle like this.
Oh, that sounds dangerous for Pookie.
And there's the radius of 15 meters. Okay, calculate the angular momentum of Pookie. So, hey, which one of these are we going to use?
R cross NV.
R cross MV? You know what? If you want to use this one, you can. To get the right answer. Just a lot more work because you got to find the moment of inertia, right? You got to do mr squared to find I, and then omega is going to be V over R, and hey, look at that. MVR. Same thing.
That was really scary.
Eureka. All right, so what's our moment of inertia, everybody?
300,000.
20,000 times. No.
Yeah, 300,000.
It is 3.
Kilograms meter squared per second.
Here,
Otherwise known as the Bruin.
let's do nice and scientific.
300
0.3 mega kilogram meters squared per second. There we go. 0.3 megas.
300 kilograms.
Why didn't?
Not kilograms.
Wait.
300,000.
Okay, that's what I got.
0.3 mega.
That's not engineering?
Stop. See, look
All
at
right.
So painful.
Now we're going to redo this. We're going to redo this, and let's say that instead, here's Pookie. Pookie's still going 20 meters per second, but now
Pookie's on a roll.
point O is over here, okay? And here's our radius right there.
Still going in a circle, right?
No, Pookie's going straight now.
Pookie likes to be
Pookie's
diverse.
moving straight. Pookie's moving on. Let's say this angle here is 30 degrees. Okay, we have two spots for Pookie. One right here and one right here. Pookie's going in a straight line at 20 meters per second. Radius is still 15 right here. This distance right here is 15. Okay, this radius, I don't know, you got to figure that one out. Okay, let's find out the angular momentum for an object moving straight. Got it?
You used a calculator to calculate. Oh my gosh.
So it's what?
300,000.
Why should I be able to do that in my head?
You ought to be able to do this in your head.
No, not this.
You ought to be able to get it in 2 seconds.
All right, right here. When Pookie is right here, what is the angular momentum right here? Angular momentum equals R cross MV, or RMV, because we have a 90-degree angle, right?
Wait, how is the angular? How is it angle straight? This might be a really dumb
Hey.
question, but it's going in a straight line.
That's correct. Shh. Don't tell. Okay, the radius is in this direction. You're moving in this direction. The angle between these two is 90. So technically it's RMV sine theta. What's the sine theta? 1. So the radius is 15, the mass is the same, everything's the same. So Pookie has an angular velocity of 0.3 mega kilogram meters squared per second.
Hey, wait.
Same as before.
Look, even if he's going straight.
Shh.
Wait,
At that point, he's going straight.
At this point, Pookie is also going straight. Right?
no.
Yes.
Yes.
Every point, he's going straight.
Vectors are always straight.
So he's not changing.
At
here.
this
It doesn't
instant
happen.
in time, Pookie has this angular momentum.
Hey,
Now-
you can't do K equals MV because you're trying to find the momentum as relative to point O.
Now look, if you took a snapshot of this, of Pookie right here, if you took a snapshot of this, flash, there's a picture. Is there any difference between this picture and this picture?
No.
None. Same velocity, same radius, same mass, same everything. Right? So even though the object is not technically going in a circle, you can still calculate its angular momentum. Okay?
But then theoretically, you could just take anything that's moving straight and say, well,
But
it's
nothing
about to
is really
turn.
moving.
That's
straight.
correct.
Therefore, it has
When you're
angular
going down the
momentum.
highway, you could say, I'm calculating my angular momentum right here, about that point. Boom.
Yeah, technically it could be zero, right?
Just like you can calculate your kinetic energy, right?
But
You
it-
can calculate your linear momentum, right?
So it's if we turn as opposed to
Uh,
angular acceleration one
No,
degree.
it still has an angular momentum there.
Okay, here we go.
It doesn't have-
What's Pookie's angular momentum right here? L equals R cross MV.
Blah, blah, blah.
That's RMV sine theta. What's the radius right here?
17 point.
Okay, let's do it. That's correct, I'm sure, but let's do this.
15 over sine.
This is
or
going to be
cosine.
15 over the sine of, no, cosine. Over the cosine of 30, right?
Yes.
15 over the cosine of 30. That's going to be 17 or something, right?
Yeah.
So here's my length. The radius is 15 over the cosine of 30, correct? The mass of Pookie stays the same, which is 1,000. The velocity of Pookie is still 20. Okay, and now we have a sine of what?
I think it's still, wouldn't it still be 90?
Would it?
Because force and radius, what's force? Where is that?
No.
It's the
R cross MV. This vector and that vector.
Okay.
Here's this vector pointing this way. Here's the radius vector pointing this way.
150.
So, yeah.
So what's that angle? 150.
No, no,
Is it 150?
no.
Yes.
It's
120.
Yeah, we're bad people.
Oh, right.
Because that's 90 and that's 30.
Yeah.
Yeah, okay.
So sine of 120. Okay, everybody.
Have a look.
Anybody got a guess on what the cosine of 30 and the sine of 120 are?
Tangent of
Anyone want to guess the same number? Anyone? Anyone?
I want to guess the same number.
Same number.
It's the same number.
Yes.
Now I want you to look at this. That's the same number. So what do we get for our angular momentum?
same thing.
0.3 mega kilogram meter squared per second. The same as before.
Madness.
Now why is that true? It's true because if you were paying attention,
Effective radius.
angular momentum R cross MV, which is technically RMV sine theta. Now, that, what's that really? Remember when we did
The
torque?
Perpendicular.
That's the perpendicular velocity. So that's really R times the perpendicular velocity. I'm sorry, not the perpendicular velocity. The perpendicular MV. The perpendicular momentum. Okay? Now, but the radius got bigger, but the perpendicular momentum gets smaller when you're out this angle, so it ends up canceling out. Or you could do this. That's R cross MV. That's the same thing as R sine theta cross MV, or times MV. What's that?
Perpendicular radius.
That's the perpendicular radius times MV. Okay, now everybody, you see this? See this car moving along? Where's its perpendicular radius?
At point 2.
Perpendicular radius is the same thing as the minimum distance between our pivot point and the path. So let's say this is you, and you're walking this way. And here's the point about which we want to figure out our moment of inertia. I keep saying moment of inertia. Angular momentum. Where's our minimum radius?
Right there.
The perpendicular radius. That's our minimum radius, right? Where's the minimum radius for Pookie?
Right there.
Right there. So it's same MV, same radius, same perpendicular radius, same angular momentum.
So,
Now here is a crazy, crazy fact.
It would have
saying
the
that
same
no matter
angular
where you
momentum
are
no
at
matter
the
where.
point, you have the same angular momentum.
That means, cool fact, if a moving object has a constant linear momentum, it will also have a constant angular momentum as well. And that holds for any arbitrary
So
point.
constant linear momentum.
If you have a constant linear momentum, if your linear momentum is not changing, then you can pick any point you want to pick the angular momentum about, and it will also not have a changing angular momentum. Okay?
That makes
It's kind of cool.
That makes sense, because if you have the same velocity, you have the same.
MV, and you're always going to have the same minimum radius to that point, no matter where you're at, right?
So Mr. Brand, if I'm in uniform circular motion,
Mhm.
my MV is the same forever,
No.
because it changes direction,
Right.
but the magnitude's the same.
MV is the same, yes. No.
Because like R
The
cross,
yeah, you're right. The magnitude of MV is the same. That's correct.
because R cross MV, they're always perpendicular.
Right.
So you'll always have the
Same.
Angular momentum. If you're in uniform circular motion, your angular momentum will remain constant. And if you have a uniform or a constant linear momentum, you will also have, by default, a constant angular momentum.
Can you show us an
So I guess
example
that
of when
doesn't
it's
make
not going to be the same?
All right, so, excellent question.
'Cause I
I'm
can
glad
picture
you
this.
asked this great and glorious question.
See if we answer that question.
On this great
Okay.
and glorious day.
How do we change linear momentum?
Hit a wall,
And what does the wall provide us with?
a change in velocity.
An outside force,
Which causes a change in.
an outside force over a time.
Impulse.
Impulse.
An impulse equals our change in momentum, right? And the direction of our impulse, oh, thank you. Thank you. Well, I just did work there, right?
Yeah.
I just broke physics again.
Wait, what happened?
All right, our impulse equals our change in momentum. So wait a minute. If this is change in angular momentum, if I want to change my angular momentum, any guesses? What will this side be? This is our linear. This is our angular equivalent. What's the
Torque.
angular equivalent of time?
Time.
Time. Nice.
Torque delta T.
What's the angular equivalent of force?
Torque.
Oh my God.
Torque.
Angular impulse.
An
Oh, it's-
angular impulse.
Wow.
If you want to change your angular momentum, you have to have an angular impulse, which means you have to have a torque,
Example?
an outside torque, applied over a given amount of time.
Like,
An example?
yes.
Like,
Okay, you got something pinned to the wall, and if you pull on the string, you're applying an outside torque, and so the angular momentum of this thing will change with time, right?
Okay.
Okay, now, this is what's really cool, everybody. Is it possible to apply a force that won't give you a torque?
yes.
Yes.
At the axis.
If the force is at the axis, you can have no torque, but you can have a force, right? Is it possible to have a torque without a force?
No.
Okay, now this is really cool. Think about that for a second.
I know, I was about to say.
Is it possible to have a torque without a force?
No.
No,
It's
because
like a penguin is a bird, but a bird is not a penguin.
Or,
Yeah.
you mean all
I
penguins?
think Batman
But
would
not all
agree.
birds are penguins.
Press.
All right, now everybody, this is the
The way
deal.
you said it.
If we have an object that has a force on it, then by default its linear momentum will change. But if we have an object that has a force on it at the pivot point,
Then there is no.
then there's no torque, and so its angular momentum will remain constant.
So like if I
Let me
was
give you an
sliding
example.
that along the axis.
Let me give you an example. How about this? If I have this object, it's pinned right here, and it's free to rotate. Okay?
But
Hang on.
force going.
No. Let's do this. I made a mistake. All right. Let's say, shoot, this will be better. You're looking at it from the top, and you have this object like this, and it's free to rotate. But there's no gravity. Gravity's not making it rotate. So you're looking at it from the top. It's pinned to a table. All right.
It's a
So
spinner
gravity's
on a
straight in.
twister.
Yeah.
We should pick Twister.
All right. No friction. That's an air trap. That you drove a nail into it, and it can spin. All right. If an object comes along and hits it, okay?
Yes.
If this object hits that, We have a collision.
Yes.
Will we have conservation of momentum?
Yes.
No. Why not?
Oh, and then
Because there's an outside force on it right here. Will we have conservation of momentum? Angular momentum. Yes. Yes, because is there an outside force? Yes. But does that force provide a torque? No.